So let's do an example, another example. Let's say that we send Michaela off in a spaceship to a planet which is 10 light years away. That's 10 light years away from the frame of reference of the Earth. Let's say that she goes in that spaceship at 0.6 c. Don't worry about acceleration. We'll just assume that we can somehow get her up to 0.6 c and then slow her down when she gets there. Keep in mind, that's not easy. So here's Michaela on her spaceship. I hope she's having fun. Let's just talk about what a light year is. Make sure we know what a light year is. A light year, or abbreviated LY, is the amount of time, right? It's the time, I'm sorry, not time. Year is time, but it's a distance. It's the distance that light travels in a year, right? So the distance that light travels in a year. Distance equals rate times time, so c year. It literally is c times 1 year, which is 3 times 10 to the 8th if we want to put it in MKS units, times a year, which is 365 days, times 24 hours, times 3,600 seconds per hour. That's going to give us meters. So this is what I get, and then I asked Siri just to check my math because the factors are 10, and this is what Siri told me. How many meters in a light year?
That would be 9, 460, 528, 405, 000, 000 meters.
What in the world is Siri talking about? She just zero. I don't know how many zeros. Anyway. Yeah, this is right. Okay, so a light year is an unimaginable number of meters, right? It's the distance light travels in a year. Light takes about 7 seconds to get to the sun, right? So that's a whole lot farther than our sun. Sorry, I'm drinking coffee, and that's a bad idea to do while I'm talking. Okay, so back to sending Michaela away to a planet that's 10 light years away according to the Earth, right? So if we give a distance, you got to say, oh, okay, now we care about the frame of reference, right? If we say it's 5 miles away or 10 light years away, we're implying that's relative to our stationary frame before we leave. I mean, that's implied. But we should also probably say, to be clear, that 10 light years is from the Earth to the planet from the Earth's frame of reference, right? In the Earth's frame of reference. Delta x is equal to 10 light years. So I haven't asked the question yet. The questions are going to be A, according to us, how long does it take her to get there? B, according to Michaela, how long does it take? And C, answer each for the round trip. Okay, I just shortened that because I was running out of space, but we want to know how long, according to somebody sitting on Earth, how long does it take Michaela to get there? According to Michaela on the spaceship, how long does it take her to get there? And then according to each of us, how long does it take for her to do the round trip back to Earth again? So I would challenge you to do this without seeing what I do first, but I'm going to go ahead and do it now so you can pause and do it on your own. So according to somebody on Earth, let's call Earth the unprimed reference frame, the rest frame, right? So Earth is O, Michaela's spaceship is O prime. Okay, so according to somebody on Earth, delta x equals v delta t, right? Distance equals rate times time. And delta x is 10 light years, v is 0.6 c, and delta t, so therefore delta t is, and I guess I should write 10 light years as 10 c years because that's what it is 0.6 c, and the c's cancel. So you don't even have to do the math to see that it's 10 over 0.6 years. That's how long it takes Michaela to get there according to somebody on Earth. That's 16.67 years. So if Michaela's 18 right now or 20, whatever, so she'll be 36, 37, 35, 36, 37 when she gets there, depending on how old she is now. Okay, so how long does it take? But is that true, right? So is that true? Right, let's go to part B, which is how long does Michaela say? See, that was a mistake, because how long does it take Michaela? How long, not does she say, but how long does it actually take her? Well, the easiest way to answer this is to say, who's got the proper time? We could go ahead and we could do a calculation for Michaela, but we can just say who's got the proper time. Michaela has the watch that is present leaving Earth, arriving at foreign planet. And so Michaela has the proper time. Michaela's time is the shortest. That means that Michaela measures T0 is T Michaela, which is delta T prime, whatever that is, whichever one of those you want to call it, any one of those. And that is whatever time we figured out here divided by gamma, because she's got the proper time. So the proper time is always going to be the time measured by somebody else divided by gamma. And so that's easy. Well, except for the fact that we haven't calculated gamma yet. So gamma is 1 over the square root of 1 minus 0.6 c over c squared, which is 1.25. If you could go ahead and plug that into your calculator. Again, the c's cancel, right? You don't have to plug in 3 times 10 to the 8th. So we get 16.67 years over 1.25, which is 13.33 years. So how old is Michaela really? If she's 20 when she leaves Earth, she's 33 when she reaches the planet, not 37. So just in case you wouldn't have seen how to do it that way, let's look at an alternative solution, right? To part B. Well, to part B, we can say, well, the proper distance, L0, is 10 light years. And we can say that Michaela measures a distance L prime. L prime equals L0 over gamma. So Michaela must measure a distance 10 light years over 1.25. So she measures a distance of 8 light years to the planet. And again, and the time that she measures is the... I always have to say distance equals rate times time. Distance equals rate times time. So that's going to be L. Oh, that was supposed to be an L prime, not an L1. L prime over V. And so that's 8 light years over 0.6 C, which is 13.33 years. Sorry, that's messy, but 13.33 years. So we can look at it from the point of view of length contraction or time dilation. Or you don't like that, then let's go ahead and just do a Lorentz transformation. So B, alternate solution. Let's go ahead and do, what did I say? A Lorentz transformation, yeah. So we know that Earth says that the distance between, that the distance of the trip, that the distance between the two events of Michaela leaving Earth and arriving at the planet, we say that that's 10 light years. So that's delta x according to the Earth. Delta x prime, the distance according to Michaela, she carries her coordinate system with her. So this is where the difficult part is figuring out what variable represents what. She carries her coordinate system with her. So she, according to her coordinate system in the primed system, never goes anywhere relative to that because her coordinate system is stuck to her spaceship, right? So her coordinate system is stuck to her spaceship so that it travels with her. So she is always at the origin of her own coordinate system. She is moving relative to the Earth's coordinate system, but she is stuck to her own coordinate system. Okay, I've said that 5 times. So delta x prime is equal to 0, and we know that I changed the color by accident. V is equal to 0.6 C, so therefore beta is 0. Just in case we need it, 0.6, and gamma is 1.25, just plugging into those. And we can go ahead and do a Lorentz transformation. Delta x prime is equal to gamma delta x minus v delta t. Sorry, it's messy. Delta t prime is gamma delta t minus v over c squared delta x. And we can go ahead and plug in to find there. We can do the first one and plug in 0 equals gamma times 10 light 10 light years minus 0.6 c times delta t, which is the unknown, and we can solve for delta t. Delta t equals 10 light years over 0.6 c, which is 16.7 years. Okay, well that was the time measured relative to Earth, because that's the unprimed frame. That was part A, right? That was part A. And then part B can be gotten from the second equation. Part B, we get delta t prime is equal to gamma 1.25 times delta t, which we just figured out was 16.7 years, minus 0.6 c over c squared times delta x, which is 10 light years, plugged in, and we find delta t is 13.3 years. Just do the math, plug it into your calculator. That comes from Lorentz transformation. So we can look at the time dilation, length contraction, or if we don't understand that or don't know how to apply that, we can just plug directly into the Lorentz transformation. You just need to be able to identify your variables before we, it's two equations, so you have to have two unknowns. So you got to identify 3 of your variables in order to determine the other 2. Any 3 variables, and you can determine the other 2. Okay, what about part C? Part C says, what about for the round trip? Now, why would anything change coming back? And nothing would. Nothing would change coming back. It should take the same, if she's going at the same speed relative to us, she's going the same distance relative to us. So coming back should be the same amount of time. So the total round trip time, according to us, is 16.67 times 2. And the total round trip time, according to her, is 13.33 times 2. So according to us, it's 33.4 years, I think, is what you get. And according to her, it's 26.6 years. So here's the key to this concept, is this is how you travel through time. There literally is such a thing as time travel. These are supposed to be years. There literally is such a thing as time travel, and you can travel through time. You can only travel forward through time. You cannot travel backwards through time. The Lorentz transformation equations actually show us that delta t prime can never be negative. I'm sorry. Well, it does show us that. I'm not sure the way I said it is exactly right. But we can always travel forward through time at a different rate than somebody else. So what happens is, and this was shown in, for example, the movie Interstellar, is if you travel at speeds close to the speed of light relative to somebody else sitting on a planet, you will age less than they will. You will age at a slower rate than they will. So we have sent Michaela away at speeds close to the speed of light. We brought her back, and she has aged 7 years less than her contemporaries on Earth. Then, let's say, who else is in the class? Dagum. Right, Dagum and Michaela are the same age when Michaela leaves. When Michaela comes back, she is 7 years younger than Dagum. They have both aged. Michaela has aged 26 years, and Dagum has aged 33 years. She's 7 years younger than Dagum. This is a phenomenon that is known in some circles as the twin paradox. Right, the twin paradox. Okay, and the reason why it's called the twin paradox, so I mean, it's a known, understood, and measured thing. that time goes differently for somebody who's moving relative to somebody else. And you can do this experiment on Earth with really accurate clocks. They've done them with atomic clocks, where they've shown that the time for a moving atomic clock goes slower than the time from a stationary atomic clock. And so they've done this experiment. They have not done this experiment with people moving in spaceships close to the speed of light, because it's extremely dangerous and costly to move somebody close to the speed of light. It's not that you can't do it. You absolutely can do it. But it's dangerous and costly. The danger is in the amount of energy that you get when you're moving close to the speed of light. So if you hit something, you're just annihilated. And the cost is where you're going to get the fuel to accelerate that much. You have that paradox of, well, I have to carry the fuel, so I get heavier in order to go faster, but now I'm heavier, it's harder to move me, so I need more fuel, right? So it's something which people are still working on solving, and if we're ever going to do interstellar travel, we're going to need to be able to travel closer to light speeds in order to make it reasonable. Because right now, in order to get to the next star system, it would take literally just the next star system, not even outside of our own galaxy. It is outside of our own solar system is what I was going to say. It is outside of our own solar system, but the next star system is, 4 light years away? But that's 4 years traveling at the speed of light. Traveling at our speeds, that's going to be generations. Generations. We're never going to be able to travel to another star system if we can't start traveling closer to the speed of light, because even at the speed of light, it's a 4-year trip to get to the next star system. So I haven't explained yet what the twin paradox is, and I will do so next time.